All right, so a summary of what we've looked at so far with differential equations. We've tried the analytic approach, and that's a great way to go if we need absolute accuracy. Remember, the idea is that we're going to separate our variables, like we did in this example, do the anti-differentiation, and if we have initial values, then we can use those to find particular solutions to the differential equation. So again, if absolute accuracy is required, then analytic is the way to go. If we want a big picture sort of idea, then slope fields are great. We can graph the differential equation by graphing those slope fields. And then again, if we need to talk about particular solutions, same idea. We start with an initial value, and we use that initial value to follow the slope field and get a general shape of the solution curve that we're interested in. So the advantage of the slope field is it gives you the big picture of all the solutions. The disadvantage is it's kind of tedious and it's also not very accurate. Another not perfectly accurate but decent method is the numerical method. And we would use that if it's too hard or perhaps impossible to solve analytically. And we're only interested in one particular solution. We don't need the entire slope field. We just need one solution. So if we don't or can't analytically solve the differential equation, then we won't or shan't get the exact answer. But what we can use is something called Euler's method. Please don't say Euler, it's Euler. Euler's method. And actually, we already understand Euler's method if we understand tangent lines. So remember that a tangent line is a local linear approximation of a curve. So if we have a starting point on our curve, in other words, an initial value that we're given, then we can use our tangent line to find a local linear approximation. The only problem with the tangent line is that our curve curves and our line does not curve. So the farther away we get from our point of tangency, in other words, the less local we are, the worse our approximation of the function is going to be. So basically, Euler's method is going to take that tangent line approximation and break it up into very, very small steps. And every time we take another step, we're going to readjust and get a new tangent line. So we can look at this graphically. Normally, we don't look at Euler's method graphically. But maybe at least at the beginning, just so we can kind of understand what's going on in the background. Here's a slope field of the differential equation dy dx equals y squared plus 1 over x plus 2. Okay, this is graphed in that Desmos slope field generator. I'm giving you the initial value of 0, negative 2. So there is a particular solution that travels through this point that satisfies this differential equation. And if I want to know what the y value is of that particular solution when x equals 4, well, the purple right here is going to show us the actual solution, which is going to give us a value right here. But what the first approximation does in this red approximation is that we start at the initial value and we say, oh, well, we know what the slope is at that point. At the point 0, 1, our slope is 1. That's easy to evaluate using our differential equation here. And we're just going to follow that slope, that rise over run of 1 over 1, and we're going to keep on following that slope until we get to an x value of 4, and we end up here. And we see that the approximate y value using that method is y equals 3. Well, clearly our answer is not y equals 3. Our answer is something less than 1/2. The y value of our target point is less than 1/2. So the problem is our curve is bending more horizontal while that tangent line keeps on heading off to higher and higher heights. So to combat that, we can try maybe perhaps using the blue method instead. So we'll start at the same initial value, of course. That's the only value we know with precise precision. So we'll head off in that same direction of slope equals 1, but I'm not going to follow that slope the entire time. When I'm halfway to x equals 4, namely x equals 2, I'm going to say, well, wait a second, I've got this new slope. I'm going to readjust my direction. I'm not going to continue to go in the rise over run of 1 over 1, because at this point right here, I have a slope of something else. Turns out at the point 2 comma 1, and we can analytically find what that slope is using this equation again, but turns out the slope at this point is 1/2. So we're going to change directions. We're going to readjust. We're going to recalibrate our slope. And from this new point, we're going to head off in this different slope of 1/2, rise of 1, run of 2. That's going to take us to a y value of 2, which again is not a great approximation, but is better than 3. It's closer to our target value than it was before. And you can see that the orange method, which is going to take 4 steps instead of 2 steps, and these steps are smaller still, is going to be even better. We're going to recalibrate our slope every time our x value increases by 1. So once again, we start at the initial value of 0, -1. Once again, we follow that slope of 1 to get to this point right here. And now we say, well, by the time we get to x equals 1, we definitely have a new slope. So we'll recalibrate earlier and head off in this direction. I think this is the slope of 1/3. And from here, we get a new slope. And again, every time we get to a new point, we go back to our differential equation and we recalculate our slope and we change directions. Now, it's hard to see a difference in the direction here because it's very slight, but we are starting to level off a little bit and a little bit more. And we can see that with this approximation, an Euler's method with 4 steps of equal size, we finally get an approximation that's at least less than 1. It's still not less than 1/2, which is what we're really looking for. But Euler's method can get better and better approximations depending on the size of our step. So we'll go ahead and find out the values of 3 and 2 and whatever this value is. And apparently this is the value we get when we plug 4 into this equation. I'm already giving you the answers here, but in the next video, we'll actually go through the calculations to figure out what Euler's method gives us for each of these 4 scenarios. Well, actually, I take it back. 3 scenarios with Euler's method, and then the purple method is going to be the 100% exact analytic method. So tune in to the next video to find out how.